Hi students, here you're going to learn about a new topic called as the convolutional codes, okay, or specifically it is called as the NKM convolutional codes, okay. We all know what is an NK linear block code, right? If you take an example of an NK, to understand what is NKM convolutional codes, let me just first remind you what is an NK linear block code. So what is an NK linear block code? We all know that in an NK linear block code, the N represents the number of the output bits or the number of the code word bits, right? Number of the bits in the actual code word. And what is K? K represents the number of the input bits or the length of the message or the number of message bits, right? So this is what the NK linear block code is. That is, a K bit message is encoded into an N bit code word. That is, every K bit message, K bits input message is encoded into an N bit output code word. This is basically the process of an NK linear block code, right? Then we learned that if this code word is being transmitted, and then when the receiver receives the code word, then the receiver will calculate the syndrome, and then blah blah blah, it goes on, and that's how the theory goes, right? So this is basically the main concept of an NK linear block code. That is, an N bit code word is encoded from an K bit input message. Or in other way of saying is that this N bit output code word is dependent only on the present K bit input message. That is what you need to understand if you need to understand the difference between an NK linear block code and a convolutional code. Okay, an NK linear block code and a convolutional code. So in a NK linear block code, the N bit output code word, as any N bit code word, depends only on the present K bits input message. Right? It depends only on the present K bits. That means whichever K bits message you input into the circuit or into the encoder, only that corresponding N bit will be generated at that particular time. Right? Because it depends only on this K bit, on the current K bits input message. So, but if you take a convolutional code, okay, in the case of an N, K, M, convolutional code, okay, here the encoder also generates an N bit output code word, but this N bit output code word depends not only on the K bits input message, but it also depends on the preceding M memory. So that is what this M stands for. M stands for the memory, or in other words we can say as that M stands for the shift register blocks. M represents the shift register blocks, or you simply call it as memory. Okay, this is what M stands for. So in NK linear convolution code, N stands for the same thing. N stands for the number of bits of the output code word, K stands for the number of input bits, and M stands for the number of shift register blocks. Okay, so this is a concept is understanding is very easy. All you have to do is simply understand a particular. The best way to make you understand this about the NKM convolution code is by using an example. Okay, so that is what I'm going to do. I'm going to use an example to explain to you the NKM convolution encoder. Okay, so let me draw. So in order to understand, let me draw you a example. Let's take a NKM convolution code. Let me take an example of 212 convolutional encoder. Okay. I'm going to draw you a N212 convolutional encoder. Okay, so if I say a 212 convolution encoder, how to draw a convolution encoder? So to draw the convolution encoder, you need two things. Okay, two things you need. One is that you need to understand the value of n and k and m. That I have understood. The value of n is equal to 2. The value of k is equal to 1, and the value of m is equal to 2. So now I found the value of n, k and m. Okay, so this is one thing you need to know if you want to draw the NKM convolutional encoder. You need to know the value of n, k and m. The second thing you need to understand is you need to know the values of the generator sequences. You need to know the values of the generator sequences. So what is the generator sequences? The generator sequences means just right now, just to make you understand, here you see the value of n is equal to 2, right? The value of n is equal to 2. Since the value of n is equal to 2, there will be two output, right? There will be two output positions, right? Or there will be two output bits will be generated. Okay, so what I'm going to do is, what I need to draw the encoder, I need the values of these three parameters, and also I need to know the values of the generator sequences, and I'm going to represent the generator sequences like this. That is g of 1 and g of 2. This is called as g of 1 and this is called as g of 2. Okay, why are there two generator sequence? Because the value of n is equal to 2. That is why there are two generator sequences. Okay, so in this example, let my generate this example just to show you how to draw the convolution encoder. I'm going to write the two different values of these generator sequences. So let g of 1. Okay, let me represent g of 1 as 1, 1, 1. Okay, let g of 1 is equal to 1, 1, 1, and let g of 2 be equal to 1, 0, 1. Okay, so this is g of 1, this is g of 2. Okay, so these are the two things I need if you want to draw the convolutional encoder. That is, you need to know the value of n, k and m, and also you need to know the generator sequences. Unless and until you know these two things, then only you can draw the actual encoder. Okay, so now I'm going to show to you how to draw this 212 convolution encoder. It's very easy. Okay, see, this is where I'm going to now explain to you what is actually this convolution encoder, or what is the significance of this n, k and m. Okay, so like I said, simply understanding that n stands for the number of output code word bits, and the m and k stands for the number of input message bits, and m represents the memory. That is not enough to make you understand what is an NKM convolution code. Okay, you need, if you really understand that, it's better you use an example. That is the best way to learn. Okay, so using an example. So in my example, this is my convolution encoder that I'm going to draw. I'm going to draw a 212 convolution encoder whose generator sequences are these two sequences. Okay, so I need these two sequences and these values to draw the encoder. So to draw that, first what I'm going to do is I'm going to draw the circuit. So first I'm going to look at the value of n. So what is the value of n? The value of n is equal to 2, which means the number of output bits is equal to 2. So what I'm going to do is I'm going to draw those two output bits there. Okay, these are the two output positions. Okay, this is one's position, this is the other position. This position I'm calling it as V of 1, and this position I'm calling it as V of 2. Okay, see how I have written this? I have put this 1 at the suffix in the upper position. Okay, just like over here, G of 1, G of 2. This is how we represent the output bits. Okay, so this is V of 1, this is V of 2. These are the two output bits. All right, so why 2? Because the value of n is equal to 2. Okay, now no matter how many output bits are there, that many XOR gates will also be there. Okay, so next thing what you're going to draw is you're going to draw the XOR functions. So again, since the output, the number of n is equal to, since the value of n is equal to 2, there will be two XOR functions. So let me draw the two XOR functions. One is over here and the other is over here. Okay, you can draw anywhere you want, most probably much more nearer to this, but it's okay. So this XOR function is for this output, and this XOR function is for this output. Okay, there, like that I drew two XOR functions. All right, now next is here the value of k is equal to 1. The value of k is equal to 1 means the number of input bit is equal to 1, which means this is my input bit. I'm going to draw it over here. This is my input bits. Okay, so see, this is what a convolution encoder means. Convolution encoder means if you look at the value of n, k and m, for every k bit, or in this case for every one bit that enters the circuit, 2 bits will be generated. That is one interesting thing about this NKM convolution encoder, that both the NK linear block code and the cyclic code word also has, but here the difference is that the way how it's being generated here, for every input bit that enters the circuit, every one bit that enters the circuit, here 2 output bits are generated simultaneously. Okay, simultaneously. So which means if you enter 1 bit into the circuit, then the 2 bits will be generated on the spot. 2 bits will be generated, and you need to record all those 2 bits. Okay, so 2 bits will be generated at a time. Okay, why 2 bits are generated? Because the value of n is equal to 2. Okay, so now what I'm going to do is I'm going to draw the shift register stages. Okay, and I'm going to draw those stages based on the value of m. So here the value of m is equal to 2, so which means I'm going to draw 2 memory blocks or 2 shift register blocks. Okay, this is one block and this is the other block. Okay, I'm going to draw. So this is a shift register. So basically I'm going to just draw the connection like this. Okay, just like this, only this much. Okay, a shift register. This is just to show the shift register stages. Okay, so this is the input bit and it's being shifted inside the shift register. The output of this shift register is connected to the input of this shift register, and the output of the shift register is now kept like this. Okay, now I will tell you what to do with all these connections. Okay, now next thing, so now what you do is you drew the first, what you did is you drew the 2-bit input, then you drew the single bit input based on the value of these, and then you draw the two shift register blocks because the value of m is equal to 2. Next, what I'm going to do is you are going to look at the value of the generator sequences. Okay, so here g of 1 is equal to 1 1 1. G of 1, that represents this output. All right, this sequence represents this output, and this is equal to 1 1 1, and 1 1 1 means this value over here. This one represents this connection, this one represents this connection, and this one represents this connection. This is the meaning of 1 1 1. G of 1 is equal to 1 1 1. Okay, look at the value G of 2. The value of G of 2 is 1 0 1. 1 0 1 means 1 0 1. So that means there is a connection over here because there is a 1. There is no connection over here because it is 0, and there is connection over here because it is 1. Okay, this connection represents this 1. This no connection represents this 0, and this connection represents this 1. This is what you call as a 212 convolutional encoder. Okay, you see, so this is this 212 convolutional encoder. Here you have a term called as the code rate. Code rate is nothing but the ratio between the number of input message bits divided by the number of the output code word bits. Okay, that is k by n. Okay, and also there is another term called as the constraint length. Okay, constraint length, and here the constraint length is represented by a capital letter K. Okay, capital letter K. So if you look over here, the code rate over here is nothing but 1 by 2, because the number of input message bit is equal to 1 and the number of output bit is equal to 2. The value of k is equal to 1 and the value of n is equal to 2. That's why this is called as 1 by 2 code rate. So the code rate is 1 by 2, and the constraint length. Okay, if you want to know what is the constraint length, you can just simply understand the constraint length is actually if one bit enters the circuit, how many times it is being shifted. That is what this means. That is how much it's being influenced, how does it affect the output bits. That is what the value of k represents. So if you look over here, if one bit enters a circuit, right, how many stages does it pass through? This stage, and this stage. So that means there are totally 1, 2, 3. So therefore the value of k is equal to 3. Okay, so a 212 convolution encoder is also called as 1/2 code rate 1/2 comma k is equal to 3 encoder. Okay, this encoder is also called as code rate equal to 1/2 and k is equal to 3 encoder. Okay, this is how we represent. This is another name for this 212 convolutional encoder. Okay, what is the meaning of k is equal to 3? K is equal to 3 means the number of the versions, of the input. You see, this is the input's current version, right? This is the present input value. This is the input value after it is being shifted once. This is the input value after it is being shifted twice. So how many times it is being shifted? It is being shifted 2 times, right? This is the present input, and this is the previous 2 input values. The previous 2 input values. There's these 2 values. That is the previous input has been shifted once, and the other previous input has been shifted twice. So that is why we say that this 2-bit code word, okay, this 2-bit code word depends on the 1-bit present input and the 2 previous input bits. That is why this is called as an NKM convolutional encoder. Okay, so now to make you understand the working of this convolutional encoder, okay, I'm going to explain to you the working of the convolutional encoder, and the best way I'm going to do that is I'm going to use an example. So here in my example, I'm going to say that my input bits that I'm going to put into my encoder is 1, 0, 1. Okay, in a convolutional encoder, the leftmost bit, okay, unlike your NK linear block code or your NK cyclic code, in a convolutional encoder, okay, in an NKM convolutional encoder, the leftmost bit represents the earliest transmission. Okay, the leftmost bit, okay, you need to understand that the leftmost bit represents the first transmission. So which means, unlike in the previous, in the NK linear block code or NK cyclic code, there and all, I always used to tell you that the rightmost bit is the first bit that you are going to transmit into the circuit. But in an NKM convolutional encoder, it is the leftmost bit that you are going to insert into the circuit. Okay, because this is basically nothing but doing nothing but a shifting operation, nothing but the shifting operation. You are not doing any division operation or multiplication operation over here. You are simply applying the shifting operation. So the first input bit of your sequence will be the first bit that is also going to enter into circuit. That is why over here, this is the first bit that you are going to transmit, this is the second bit you are going to transmit, and this is the third bit you are going to transmit. Okay, so I'm going to use my same convolutional encoder. Okay, let me draw that same convolutional encoder. Okay, so that I can show you how this working is done. Okay, okay, so this is U. Okay, this is the U. This is where you are going to transmit these 3 bits. Okay, you are going to transmit 1, 0, 1 over here. First this one you will transmit, then this 0, then this 1. Okay, and then what you're going to do is you are going to find the corresponding value of your output bits. Okay, this is what you're going to do, right? So this is, let me give a name for this. Let me call this as SR1, and I will call this as SR2 for now. Okay, these are the 2 names of the shift registers. Okay, so initially we all know that for shift registers, before starting the circuit, the values of the shift registers are always initialized to 0, right? There's no value, so we will flush it to 0. So how is the working of a 212 convolution encoder is. Okay, let me discuss you that working. So first thing was what it do. So we all know that this is the shift register, and the value of the shift register is represented over here. Okay, that is the output of the shift register represents the value inside the shift register. Okay, so that means if you want to know the value of SR1, that is the value over here. If you want to know the value of SR2, that is the value over here, right? And this is the input bit, right? So if you want to understand the explanation, first let me draw it in terms of a table. Okay, so this is my shift cycle. In my table, the first column will be the shift cycle, the second column will be nothing but U, the third column will be the contents of the shift register. Okay, and next you have is the output. So here there are two outputs, so which means I'm going to mark those two outputs in our table. Okay, so now I'm going to explain to you the working. So you all know, first thing what I'm going to do is I'm going to put a 1 over here. So first the 1 will be applied at the input. Okay, we already know that the value of the shift register SR1 and SR2, the value inside this two shift register is clean, right? It is resetted, so therefore the values will be 0. So therefore in the first shift cycle the input bit is 1 and the shift registers are all 0 0 0. Okay, so what is the value of V of 1? You can see over here, if you look in the circuit, V of 1 is nothing but the input bit XORing with the first shift register and XORing with the second shift register, right? That is the value of V of 1. That is this XOR this XOR this. XOR means you can just think of it as a modulo 2 addition. Okay, that means 1 plus 0 plus 0. 1 plus 0 plus 0. What is 1 plus 0 plus 0? It is 1. Okay. Now, what is the value of V of 2? The value of V of 2, if you look over here, V of 2 is the input bit XORed with the shift register 2, right? With the second shift register. So, input bit XORing with the output of the second shift register. That is 1 plus 0. 1 plus 0 is also 1 plus 0 is also equal to 1. So, this is your first output. That is, when you apply the first input bit into the circuit, okay, the input bit is over here, it is not even being shifted, it is not even being shifted into the circuit, it is just been applied at the input. So as soon as when you apply the input over here, immediately you will get an output, right? And that output value is 1 1. This is the first output set that you will get. Okay, now on the second shift cycle, what happens is that this input bit is now being shifted. Okay, so what happens when this input is being shifted? When it's being shifted, then this 1 goes over here, this 0 will be discarded, this 0 will be shifted over here, and this 0, the second bit, will enter the circuit. So that means the next bit will be 0, that this 0 represents the second bit in the sequence, and then the previous bit will be shifted to the over here. Okay, the previous bit will be shifted over here, and this 0 is being shifted over here, and this 0 is discarded. Okay, so now what is the new output that you will get? What is the value of V of 1? V of 1 is this value plus this value plus this value, right? That is 0 plus 1 plus 0. 0 plus 1 plus 0, which is 1. And what is the value of V of 2? The value of V of 2 is U plus the input bit plus the second shift register, which is 0 plus 0, which is 0. So this is the value of the second output. That is 1 0. First you will get 1 1, then you get 1 0. Okay. Now what happens in the third cycle? In the third cycle, the third bit will enter the circuit. Okay. This 0 will be discarded. This 1 will be shifted over here. This 0 will be shifted over here, and this 1 will be applied to the input, which means the input will now be, or the stage of this circuit will become 1. Here it becomes 1. Here it becomes 0, and here it becomes 1. 1 0 1. Here it becomes 1. Here it becomes 0. Here it becomes 1. Okay. So now what is the value of V of 1? V of 1 is this connection XORing with this connection, XORing this connection. That is 1 plus 0 plus 1. 1 plus 0 plus 1. What is 1 plus 0 plus 1? It is 0. Okay. And what is the value of V of 2? V of 2 is the input bit XORing with the second shift register, which is 1 plus 1, which is 0. So your third output value is 0, 0. Your first output value is 1, 1. The second output value is 1, 0. The third output value is 0, 0. What happens in the fourth cycle? In the fourth cycle, this 1 will be discarded. This 0 will be shifted over here. This 1 will be shifted over here. And since you have no other input to give, your input, you're only giving 1, 0, 1, right? So there's no more input for you to give. So you will be applying nothing but 0 itself. Okay. So now what will be your output? So that means this, which means is that this 1 will be discarded. This 0 will come over here. So this will become 0. And this 1 will come over here. So this will become 1. And there's no input to give over here. All the inputs you have already given. So you're going to give a 0. So you will get 0, 1, 0 over here. 0, 1, 0. So if you, what is the value of V of 1? 0 plus 1 plus 0. 0 plus 1 plus 0, which is 1. And what is the value of V of 2? It is the value of the input bit plus the second shift register, which is 0 plus 0, right? 0 plus 0, which is 0. Okay. Now what happens is that on the next shift cycle, okay, on the next shift cycle, this 0 will be discarded. This 1 will be shifted over here. This 0 will be shifted over here. And since you have no more input to give, you will also apply another 0 over here. So what is the value of V of 1? The value of V of 1 is 1, and the value of V of 2 is also 1. Okay. So this is what happens. You see, so what you basically did is that in the circuit, you got 5 different outputs. Okay. How did you get the 5 different outputs? The 5 different outputs you got is because first you applied the length of the, you applied the information sequence. All right. You applied these bits one bit at a time, that is 1, 0, 1. First you applied this one, then you applied this 0, then you applied this 1. Okay. And after applying this information sequence, what you did is you try to flush the circuit, right? You try to flush, or you try to clean the circuit by wiping out all its contents. And how you do that is by simply inserting the extra zeros into the input. So how many zeros do you need to input it? You need to input 2 of them, because you have 2 shift registers, right? You have 2 shift register blocks. So which means in order to flush out the contents of these 2 shift registers, you put an additional zeros into it. So there are 2 shift register blocks. So you, so along with 101, you apply 2 more zeros in order to clean the circuit. That is why the content of the circuit will be, so now after the cycle, the content of the shift register will become 0, 0. This one will be discarded. This 0 will come over here. Okay. This 0 will come over here. This 0 will be shifted, and then no more input bits are giving, so it will be 0. So from here onwards, the output will be 0. So that is why you got 5 different output values. So what is your output value? Your output value is 1, 1, comma, 1, 0, comma, 0, 0, comma, 1, 0, comma, 1, 1. This is how you represent the output bits, right? Why there are 2 of them? There are 2 of them because the value of n is equal to 2. Okay, the value of k is equal to 1. That is why you are only giving the input at 1 bit at a time. So every 1 bit that enters a circuit, every 1 bit, okay, let it be a 1 or a 0, let it be a logic 1 or logic 0, every 1 bit that enters a circuit, you will get 2 output bits simultaneously. Okay, so since the length of the information sequence is equal to 3 and the number of shift registers equal to 2, you will get 5 different values. Okay, that is, first you apply the information sequence, followed by clearing the shift registers by applying the respective number of zeros. And this is how you would explain the working of the convolutional encoder. Okay.